This topic will cover transport layer sections 6.6.6 to 6.6.6. So this will cover fast segment processing. This section will look at some specific methods for speeding up segment processing. Segment processing overhead has two components, overhead per segment and overhead per byte. Both of these must be attacked. The key to fast segment processing is to separate out the normal successful case, or one-way data transfer. In order to make the protocols run fast, the designer must minimize processing time when everything goes right, while minimizing processing time when error occurs is secondary. Okay, so there are two figures. The one on the left is figure 6/51. The sending process traps into the kernel to do the send. And the first thing the transport entity does is test to see if this is the normal case. And then the state is established. The other side is trying to close the connection. A regular full section is being sent, and enough window space is available at the receiver. If all conditions are met, no further tests are needed, and the fast path through the sending transport entity can be taken. This path is taken most of the time, and it is standard. The right side shows the fast path processing from the receiving side. The first thing it does is locate the connection record for the incoming segment. Then the segment is checked to see if the normal one, it's the normal one. And then the state is established. No connections are closed, and the segment becomes a full segment. These tests take a handful of instructions. If conditions are met, a special fast path TCP procedure is called. The fast path updates the connection record and copies data to the server. Okay, now looking at this figure 6/52, this is basically a TCP header. The shaded parts show the fields that are the same between consecutive segments on a one-way flow. All the sending transport entity copies the 5 words from the prototype header into the output buffer, and then it fills in the next sequence number. It does it by copying it from a word to memory, and then computes the checksum and increments the sequence number in memory. Then the header and data are transferred to a special IP procedure for sending a regular maximum segment. The IP copies its 5-word prototype header into the buffer, fills in the identification field, and computes its checksum. The packet is then ready for transmission. Okay, so 6.6.5 is the header compression. Header compression is used to reduce the bandwidth taken over links by higher layer protocol headers. Headers are rather short and do not compress well individually. Header compression obtained large gains through the knowledge of protocol format. So one of the first schemes was designed by von Jacobson in 1990. This scheme was used for compressing TCP/IP headers over slow serial links. It is able to compress a TCP/IP header of 40 bytes down to 3 bytes. The trick is similar, shown in the figure 6/52 from the previous slide, which shows the TCP header. Many of the header fields do not change from packet to packet as there is no need. With a header compression, it is possible to have simple headers in higher layer protocols and compact encodings over low bandwidth links. ROHC, which stands for Robust Header Compression, is a modern version that is defined as a framework in RFC 5795. It is designed to tolerate the loss that can occur on wireless links. There is a profile for each set of protocols to be compressed, such as IP, UDP, and RTP. This is a typical operation. So basically the ROHC reduces IP, UDP, RDP headers from 40 bytes to 1 to 3 bytes. So in short, header compression can help reduce the amount of data that is sent and reduce transmission delay. Off to 6.6.6 protocols for long fat networks. Long fat networks, also known as fat pipes, have been around since the 1990s. These are basically fast networks that have long delay for bandwidth and can transmit data over long distances. However, this can cause many problems. Some of these problems include the following. So the first one being that many protocols use 32-bit sequence numbers. Many protocol designers assumed without stating it that the time required to use up the entire sequence space would greatly exceed the maximum packet lifetime. The size of the flow control window must be greatly increased. In order to have good performance, the receiver's window must be at least as large as the bandwidth delay product and substantially larger because the receiver may not respond instantly. So for example, a transcontinental gigabit line requires at least 5 megabytes. And then simple retransmission schemes such as the Go Back-N protocol perform poorly on lines with a large bandwidth delay product. The resources can be wasted using these schemes. Gigabit lines are fundamentally different from megabit lines in that long gigabit lines are delay limited rather than bandwidth limited. Also, gigabit lines tend to be more expensive. And then the last problem is that communication speeds have improved faster than computing speeds. So in wireless networks, protocol processing can be an issue due to hardware and CPU design because there's so many different design layouts for those. Okay, and then here's a figure 6-54. This basically shows the process of a 64 kilobyte burst of data sent from San Diego to Boston. So if you look at point A, there's a link that starts initially at t = 0. That's when the pipe is empty. And then you go to point B. That's when all the segments or data are out on a fiber tunnel. After 500 microseconds, and then this lead segment will be in deep part of Southern California. However, the transmitter will stop for a window update. And then here we get to point C. And this is after 20 microsecond mark. The lead segment hits Boston and then it is acknowledged. And then finally at point D, after 40 microseconds, the first acknowledgement gets back to the sender, and then the second burst of data is transmitted. So overall, the efficiency is 1.25 M seconds out of 100, or about 1.25%.